Today we're going to be going over the high frequency analysis of a common source transistor with amplifier with a active load. So this might look a little familiar. It's essentially just a regular common source, but instead of a resistor hooked up to the drain up there, it's a transistor that's just in saturation. So we're not going to do the biasing analysis because you guys should know how to do that by now. We're just going to do the small frequency and then the high frequency analysis. So we're assuming that we know GM1, GM2, R01, and R02 from doing our DC analysis or biasing analysis. We'll get that. And we're going to look at these transistors and determine the gain and their poles contributed from CGS and CGD. So we're going to start out with small frequency, low frequency, whatever you want to call it. And let's call this 1, let's call this 2. To that, we're going to have our VGS here. This is VN. Have our GM, VGS. We're going to have R01. We're going to have R02. This is V out. R01 comes from the NMOS, R02 comes from the PMOS. And we can change R02 based on what this V bias is. Also, you could have this just being a current mirror, and you'd end up with a similar setup. There would just be a certain voltage here, and it'd be biasing this to get this into a resistor. So if like in the lab you need to do something like this and you don't want to have voltage sources, you just will wire up a current mirror to this and it would bias this on. So V out here is equal to negative GM VGS. V's in parallel, which is R01, R02 over R01 plus R02. So V out over Vn equals negative GM R01, R02 over R01 plus R02. And we can call this whole thing right here just R out. And so then our gain here is just equal to negative GM R out. That's the form we normally get, what we know from doing previous small frequency analysis. So now that we have this, we need to do high frequency analysis. And at high frequency analysis, we have to take into account CGS and CGD. Because of those high frequencies, the CGS and CGD are going to start having impedances. So we'll set up our circuit here. We're going to have this VGS over here, we'll call this V in. And this is going to have some small resistance R sig. This is just built in to this generator. There's always a little bit of resistance between the voltage and the node that's hooked up to. And then we're going to have CGS here. We're going to have CGD here. Have our GM, VGS right here. Then I'm just going to call this R out. R out is R01 and R02 in parallel. It's essentially what the V out sees for resistance. And then we'll have our CL here. And we're also going to have a CGD from 2. So it's just a little extra capacitance down here. And this CGD is just because when we put this in small signal, if you can imagine just like a CGD being right here, and right, because a PMOS is the same as the NMOS, high frequency, low frequency, it's just upside down. And going from the low frequency model to the high frequency model, you just need to add your capacitors in here, and you add an R sig because now there's a path. There's a couple paths, but so this is at ground, this is at ground, this is our V out. V out to ground is connected by CGS2 up here. CGD2, excuse me. So we just added in down here. And so now we have our input section here and our output section here, but they're connected together by this capacitor, and that makes figuring out the transfer function here kind of a pain. So we're going to do something called the Miller theorem. And essentially what the Miller theorem is that if you have some impedance Z, and this is ground, and this is ground, with a current I through it, V in, V out over V in equals K, that you can take this and turn it into this. As long as the current is the same. So, how you do this? Well, first of all, you get Zi equals Z over 1 minus K, and you get Z2 equals Z over 1 minus 1 over K. And so that's just doing this, keeping current equal to this, and calculating it out. Now, so if this Z is a capacitor, and we know, oh, sorry. I didn't realize I was off the page. So I'll go back over. Some impedance here that's connecting V in and V out. We break it up into 2 capacitors connected to ground. We calculate it out so that the voltage on each node and the current through each node is the same. So if you look at it from outside, it's exactly the same. And all we're doing is changing around what's inside of it. And these are the equations we use to do that. So if these are capacitances, and we know that Z for a capacitor is equal to 1 over SC, that means that to calculate out C1 based on some C, it's just C times 1 minus K, and C2 equals C times 1 minus 1 over K. And so this K in our case is just going to be the gain we found from our small signal. Now, we can assume this to be large because the gain from common source amplifiers is typically very large, usually at least 100. You're usually going from millivolts, microvolts to millivolts, or something on the scale like that. So we can simplify this out, and this is negative, so we'll just plug this in here. C1 here is equal to CGD, because that's the one we're splitting, times 1 plus GM R out and C2 equals CGD times 1 minus 1 over GM R out, 1 plus. If we assume this is large, this just goes to 0, and this is approximately equal to CGD. So now we're going to take this transform we did, turning this into 2, and we're going to split it up into an input side and an output side. So for the input side, we have our V in here, we have an R sig here, and then we have our CGS and our C1. So let's call this C in. It's equal to CGS plus C1. C1 is equal to CGD times 1 plus GM R out. So then this is our sig. To go from V in to VGS here, it's just a voltage divider where VGS is equal to C1 over SC in over R sig plus 1 over SC in, so times V in. So then we get VGS over V in equals 1 over SC in R sig plus 1. So remember, our first pole is just 1 over C in R sig. And you'll notice that 1 over capacitance times resistance is tau. This is always going to be the form. Occasionally you'll have other variables in there, but 1 over capacitance times resistance is always going to be where your poles or zeros are at. You'll remember, like, this is the time constant. It always takes this form. If you flip it, it will take this form, but it will be a 0 instead of a pole. So now we have our pole from the input, so we need to get the pole from the output. So for the output, we have R out here, let's call this C out. C out is equal to CL plus CGD2 plus CGD1. This is equal to C2. Remember, we said this was approximately this, so I just subbed that in for that. So our V out here is just going to be the current times the impedance. So this impedance is 1 over Z out, which is just the output impedance, equals 1 over R out plus SC out, which equals 1 plus SC out, R out, all over R out. And then V out equals negative GM VGS times R out all over 1 plus SC out R out. And we move the VGS over to the V out and we get V out over VGS equals negative GM R out 1 over 1 plus SC out R out. So our second pole is 1 over C out R out. So do you see the trend that's happening here? Essentially, the way to calculate the poles, an easy way without actually doing out all the work, is to look at your input nodes and your output nodes and sum up all the capacitance and sum out all the resistance, and 1 over those two values multiplied is your pole. And so this works for a whole lot of circuits. Sometimes there are little twists to it, but it's usually in this form, and it's essentially just the impedance that the output or the input is seeing, and that is causing it to have a pole. If we put this all together to get V out over V in, you'll see we get minus GM R out, which is our low frequency gain, times 1 over 1 plus S C out R out, times 1 over 1 plus S C in R sig. So you see it's just our low frequency gain times omega P2 omega P1. The pole forms. Now technically there should be a 0 in this as well, but because we did node pole here, we're ignoring it, and we can justify this because we'll go back to what we had before. The fact is that you can get a current through your input to ground, and that current will come out and will contribute to the current across your output impedances, so we got our V out by multiplying the current by the output impedance. Well, there's an input current here, I in, but we're assuming that's very small because both of these capacitors are very large, especially C1, because C1 just scales directly with gain, and we designed the gain to be large. So the current that's actually coming in through here is extremely small, which causes the 0 to be very large, which means that unless you're at very high frequency, the 0 isn't going to matter a lot. And if you're at that high frequency, these two poles have already attenuated your signal significantly. So the fact that there is a 0 there does not affect it that much. If you're doing really high frequency stuff, you will have to analyze this, and that requires you to do a full circuit analysis. But for this class, doing node pole is fine.